Hi, I'm Grace Fan. I'm a PhD candidate at Northeastern University. Today, I'm here to talk about Starmie, our work on semantics-aware dataset discovery from data lakes with contextualized column-based representation learning. This is work done with Jin Wang, Yuliang Li, and Dan Zhang from Megagon Labs, as well as with Professor Renée Miller from Northeastern University. Suppose a data scientist comes to us with a query table they have about different states, the capital of the states, and the year the city became the capital. And she wants to find a table that is related to her table about different states. One option she has is that she can perform keyword search over the metadata of data lake tables to find the relevant tables that she's looking for. And the search over metadata of data lake tables, or column names or table names, presents itself as an issue in the context of data lakes, since metadata is often very unreliable in that it's often missing, inconsistent, and very generally poorly managed. And also, there is an issue of, does she know exactly what kind of relevant table she is looking for? Unless she sifts through millions of tables from the data lake, it is difficult to know exactly what kind of relevant table she is seeking in terms of relevant to her query table queue. This leads to our problem of finding semantically unionable tables from the data lake to a given query table queue. And by semantically unionable, we mean we want to find data lake tables that can extend query table queue with additional rows that preserve the same semantics as the existing rows in the query table queue. So for example, if we have the same query table about different states, one possible semantically unionable table from the data lake is this table with different states, their cities, the date the city became the capital, and the population size. And notice here that the column names aren't exactly consistent with those of the query table queue, and the column set isn't the same, but the semantics of each row in data lake table T are the same semantics as those in query table Q, and can thus extend Q with additional rows. There is a line of related works for unionable table search. However, a lot of these works focus on column or attribute unionability when finding unionable tables. So for example, if we have the same query table Q and we know that table T1, the same table as before, is expected to be a semantically unionable table, and we have another table from the data lake T2 that is about birds, the date they were seen, and where they were seen. If we look only at attribute unionability, we can see that T2 has columns date and location aligned with columns year and state from query table Q. And so table T2 could be falsely returned as semantically unionable to query table Q. And also, if we look at binary relationships between attributes, which was proposed in a newer work called Santos, we can see that T2 has a binary relationship between date and location that is also shared between state and year in query table Q, and can again return T2 as a false positive when returning it as a unionable table. So instead of returning T2, a table about birds, to a table query table Q about different states, we want to look at the entire context of the table to see what is this row or what is this table referring to exactly. So we need to look at the context from the entire table to capture the semantics of each column to correctly return T1 as a unionable table and not return T2 as a unionable table. This leads to our work called Starmie, which focuses on the problem of semantic table union search, in that in addition to finding column semantics and binary relationship semantics when finding unionable tables, we also want to use the entire table context to find these tables. And to do so, we leverage a natural language approach in which we use a language model that uses the table context to learn the semantics of attributes and of the table. So in Starmie, in the entire pipeline, in the offline stage, we are given data lake tables in which we perform pre-training, contrastive self-supervised training, and we run multi-column encoders to encode the columns into high-dimensional vectors, and we store these vectors into indices for efficient processing in the online phase. And in the online phase, we are given a query table in which we run model inference to get the vectors for each of the columns in the query table. And we compare all of the contextualized embeddings from the data lake table with those of the query table, and we find the vectors that have high cosine similarity with those of the query table to retrieve the top k unionable tables to the user. So in using pre-trained language models, a big part of having high accuracy is fine-tuning the model. However, fine-tuning requires a lot of manually labeled training data, which is not entirely feasible in the context of data lakes with its massive size and heterogeneity. So this leads us to consider a self-supervised technique, which we use one from computer vision called contrastive learning. And in contrastive learning, we can learn representations without any external labels, such that similar items are close together in the representation space and different items are far apart. For example, if we have column X, we can generate two views of the same column X to generate the positive samples that we need. So we can have the original column X and apply a data augmentation operator to create a different view that has the same semantics as column X, and X original and X augmented become the positive samples that we need. And for the negative samples, this is all other pairs of columns in the data lake. So in this way, we can use contrastive learning to learn our column representations. So from contrastive learning, we can figure out that, okay, this column here is about year. But what is year in reference to? Is it the year that the capital became the capital of the state? Or is it the year that a bird was seen? So in order to encode the context of the entire table, we want to leverage multi-column table models such that we serialize and concatenate all of the values from a table and input them into table transformers, which can then learn and produce contextualized column embeddings. And in this way, our column representations are now context-aware. To go into more a specific example for contrastive learning for table representations, if we want to produce positive and negative samples just from the data itself without any external labels, for positive samples, we generate aligned pairs of columns in different views of the tables such that the different views preserve the same semantics of the original table. To do so, we can apply table-level augmentation operators to produce these semantic preserving views. So for example, if we have the same table as before with the states, we can generate two views of the same column X, in this case it's state, by applying a table-level augmentation operator to the table. For example, we can drop this column to capital to have just state and the year, and we say this column state is still the same semantics as the previous, as the original column. So this produces our positive samples, which consists of the same columns from two views of the same table. And for negative samples, these consist of all other pairs of columns. These include the unaligned columns from the same table. So for example, state and the year become negative samples. And the negative samples also include columns from distinct tables. So for example, state and bird name from a different table also become negative samples. So moving on to the online query processing phase, in order to expedite this attribute retrieval from data lake, we leverage approximate indexing. And there is state-of-the-art hash-based indexing, locality-sensitive hash indexing, which we experiment with when running Starmie. But we also use a newer indexing approach called Hierarchical Navigable Small World Index, or HNSW index, which is a graph-based indexing approach, which we also experiment with for Starmie. So now that we have all of our techniques, we now segue into our experiments. For the benchmarks that we experiment with, we have 3 benchmarks for effectiveness and 2 benchmarks for scalability. For effectiveness, we have benchmarks that range from 550 tables to 5,000 tables. And each of these three benchmarks have their own labeled ground truth that accompany them. And for our two scalability benchmarks, these have 11,000 tables as well as 50 million tables from the WDC Web Table Corpus. And these are to experiment indexing approaches. For our baselines to run effectiveness experiments, we have single column, which is a single column variation of Starmie. And in this, we use the same encoder as Starmie, but instead of using the multi-column table encoder, we encode columns with no context. In this way, we can see how well Starmie performs if we have the context of the table. And one other notable baseline is Santos, which is a state-of-the-art table union search approach, which considers both column semantics as well as binary relationship semantics between columns when finding unionable tables. So for our effectiveness experiments, we see that for the Santos small benchmark, we retrieve the top 10 unionable tables to a given query table. And we see that our approach Starmie achieves a mean average precision of 99% and a recall score of 74%. And note here that in a lot of the cases for query tables, K, or the top 10 results that we retrieve, this value K is less than the number of expected results as defined by the ground truth. So this leads to the ideal recall that we can achieve being lower than 100%. And in this case, our ideal recall, or the best recall that we can achieve, is actually 75%. So Starmie's recall is pretty close to ideal recall. And Starmie outperforms Santos, or the state-of-the-art baseline, by 6.8% in mean average precision, and by 6.8% in recall as well. And compared to the single column variation, or the first row, single call, Starmie outperforms single call by 11% in mean average precision and by 25% in recall. So Starmie proves to be very effective in using the table context to accurately find the unionable tables. For scalability experiments, we see how well Starmie performs in terms of query time when using LSH index and when using the newer HNSW index. To do so, we tune the data lake size from the WDC Web Table Corpus from 200,000 tables to its full size of 50 million tables. And we see that when we use LSH index, it actually times out after the data lake size exceeds 10 million tables, in that it doesn't run even after 24 hours. But if we use the HNSW index, it consistently has a query time of 60 milliseconds throughout all of the data lake sizes, even up to its full size of 50 million tables, showing that HNSW index allows Starmie to scale pretty well. So in conclusion, Starmie is the first end-to-end contrastive learning framework that uses a multi-column table transformer to learn contextualized column representations in an unsupervised manner for the main use case of the table union search problem. And from our effectiveness experiments, we see that Starmie outperforms the state-of-the-art baseline, or Santos, by 6.8% in mean average precision and in recall. And from our scalability experiments, we see that Starmie using HNSW index actually has a 400 times performance gain over using the LSH index. And in addition, Starmie can also be effectively applied to other data discovery tasks, like finding joinable tables for downstream machine learning tasks. And for more information, please feel free to visit our full paper online. Thank you so much.